Before we jump in, just a quick word about LIAPG. We are a non-for-profit professional organization serving geologists in the broader geoscience community across Long Island and Metro New York area. Our mission is to support the professional and business needs of our members and to do that in a way that is diverse, inclusive, and equitable. So we want everybody to feel welcome, heard, and valued in our meetings, our events, and any leadership opportunities that are presented. With that, I'll just run through a quick, some quick slides with some LIAPG updates and then introduce today's speaker. So thank you to our 2026 LIAPG corporate sponsors. I wanted to start out with that. Your support helps keep LIAPG programming accessible, these events, support student initiatives, continue building value for our members. If you're here representing a sponsor, thank you. We appreciate it. And if your company is interested in sponsoring LIAPG, please reach out to us. We are happy to share the sponsorship options. Next. Just a few quick organizational reminders. Our board meetings are held monthly, typically the first Wednesdays. We hold those either both virtually and in person. Our next meeting is Wednesday, February 4th. We also maintain some employment opportunities on our website. So please use it and send us your postings if you have any. And just to put some names to our current officers, they're up there. Again, my name is Regina Bykov. I'm serving as president. Chris Wenzel is serving as the vice president this year. Our treasurer is Cheryl Neary, and our secretary is Artemis Nemencox. I don't know if I say that right, Arnie. I'm sorry. I think I always butcher your name. And then a list of our current board members. There are 6 other board members at this time. Thank you to Chris and Jennifer for helping out on this presentation as well. 2026 committees. This is a new initiative this year. We formed several committees: the Finance Committee, Membership Committee, Outreach, Scholarship, Event Planning, and Newsletter and Communications. And the members of those committees are listed on this page. If you do have any interest in getting more involved, committees might be a really good option. Even a small contribution, helping with a single event, outreach effort, contributing to a newsletter item, that makes a difference to us. So if you're interested, please reach out after this webinar or anytime, and we'll connect you with the committee that you want to get involved in. Okay, upcoming events. Looking ahead to programming, we do have our quarterly dinner meetings, usually on the 3rd Thursday of the month. And that would be March, June, September, and December. Those are driven by participation and being able to get speakers. So if you're interested in presenting either at an in-person dinner event or one of these webinars, please let us know. Obviously, your support is what allows us to keep programming going. So our next dinner meeting, we don't have a location nailed down yet, so to be determined. But we do have a speaker, Dr. Fred Stum from USGS. He's presenting on the updated hydrogeologic framework and the extent of saltwater intrusion across Kings, Queens, Nassau, and Suffolk counties based on recent exploration drilling. This is a follow-up to a presentation that he had given last year. So I think there was a lot of interest in that presentation last year, and so this will be a really nice kind of follow-up and add on to that. We do have some revamped membership benefits for those that are not aware. There's no change in annual dues. Membership renewals are currently underway. So just a quick refresher, all of the benefits are up here. If you have any questions, let me know or let any of us know. We have the corporate memberships, Feldspar, which is practicing professionals in related fields, individuals. fluorite educators and regulators, and then gypsum who students and retirees. If you haven't renewed yet, please do so. They are what keeps our programs running, and they help expand what we have to offer to our members. So in other news, again, we have our renewals ongoing, and they've been restructured with some added benefits. Our Q1 2026 newsletter, the Glacial Gazette, is open for content. So if you have a short article, a case study, a project note, a professional update, we'd love submissions. Again, if there are some benefits with your renewals and your memberships regarding the newsletter. So if you have questions about that, please reach out to us. We are probably publishing that, well, we're publishing that in March of this year. So again, ongoing, we're looking for content. Anything you have would be helpful. And we're also planning some field trips and member appreciation events this year again. So once we have those scheduled, we of course will put out an event announcement. And I think that the biggest new initiative that we have this year is our 2026 scholarship initiative. We're launching the Gil Hansen Memorial Geoscience Scholarship for the 2026 through 2027 academic year. We're still working out some of those details. And thank you to Brett Bennington and Lars Aim for helping us with that. They are two academics that have joined our board. And of course, we'll share more details soon on how students can apply and how members can support that effort. I'm going to turn over this slide to Chris, who is currently serving as the New York State Council of Professional Geologists president. And he's going to give us an update on where they stand.
Thank you, Regina. Real quick, high-level update on some things going on with the New York State Council. We have a number of online trainings that everybody's welcome to participate in coming up. The first is continuing education for PDH evaluator training, and that is we have a group of people that when you submit a presentation to us for review and approval of a PDH credit hour or more, we do that. If you're interested in getting involved, you should reach out to us, but this training is essential to be participating in that. So that's a noontime webinar on February 4th. For those of you who seek PDH credit to keep your license in force, you know that you have to take an ethics presentation once every 3 years. That'll be at noon on the 8th. We've got a new presentation that's going to be, co-hosted and put on by the New York State Department of Ed for PG applications. So if you're somebody or know somebody who's interested in getting their PG license, this is about how do you fill out the application? What do you do? That's on April 15th at noon. And then as we begin to ramp up our public student outreach, we'll be doing a student webinar around May 6th, time to be determined. And this is to talk about what the council does, what it's like to be a professional geologist, what it's like to work in this field, as well as what are the requirements of licensure. So these all you can go to our website and check that out. You can also connect with us via LinkedIn, and you can see in the upper right there's a QR code you can scan, and that'll take you to the LinkedIn website. There'll also be we're co-hosting a seminar with Midwest Geoscience at Vassar College on May 13th, 14th, and 15th. Anybody who doesn't know where Vassar is, it's in Poughkeepsie, so not far from this area. Geology Days, the 5th annual, will be on November 8th through the 10th, coming in the fall. A few other things we're doing. We're updating and revising our website to make it more user-friendly and functional, and adding some features to that. As I mentioned, we'll be ramping up our outreach efforts this year. That's a focus. Reach out to students and universities and colleges and help folks understand what it is we do. Um, we're also working with our stakeholders to reestablish the New York State geologist role. I'm not going to get into that here, but if you're interested, reach out. We can explain it better. Um, our lobbyist continues to advance key legislation in Albany, both in the Assembly and the Senate. There's a few bills that we've been watching closely and help advance, like the grandfather correction bill. And then lastly, much like LIPG, we have a quarterly newsletter, and we really encourage everybody to consider submitting a short article. Everybody's welcome to. The next one will be published in March, and submissions are due by February 27th. Thank you, Regina.
Thanks, Chris. And with that, thank you everyone for letting me and Chris run through those updates. I'm excited to introduce today's presentation, episode 6, Return of the Samples, presented by Caitlin Ahrens, PhD from Planetary Geology, Geophysics, and Geochemistry Lab at NASA Flight Center. And just a reminder, if you did sign up for PDH credits, please make sure that you were signed in for the full presentation and the quiz, and that you enter your answers in the chat bar for the quiz. Additionally, if you have any questions during the presentation, please enter them in the chat bar, and we will ask these at the end of the presentation, unless Caitlin has a different preference. So with that, Caitlin, thank you for joining us. We're looking forward to the talk. For everybody attending, again, feel free to put questions in the chat as they come, and we'll make sure we capture them at the end. So Caitlin, take it away.
Great. Thank you so much for having me this evening. Very excited to talk about sample return missions. What does that mean for geologists? What does that mean for space geology as well? So very excited. So this is my second time presenting for you folks, and Chris reached out to me first and was like, "Can you come back?" It's like, "Yes, absolutely." But I need this, you know what? You would think I would understand how to do a share after all these years, and still no, it's still a mystery to me. Okay, here we go. Right, okay. So no worries that it's like episode 6. I'm just trying to be funny about Star Wars here. This is not my 6th presentation of a series or anything. So just don't worry about that of like 6 times. Who are you? But essentially, though, what I'm going to be presenting on this evening, though, is samples. How did we get samples from other planets and bodies and everything, though? And so, I mean, I'm also a bit of a Star Wars fan, so feel free to include your own intro music, if you will. But it all comes into how do we sample? Why do we sample? Where do we sample as well? Because every single bit of the solar system is very different. And so sampling these different bodies requires different means of not just getting there and coming back, which is a whole different issue, but how do you scoop up that kind of material? Is it robotic? Is it human based and so on? So also, how do these samples going to tell us about how to actually live in space at some point? Now, am I saying we're going to be start living um fully like on Moon and Mars anytime soon? No. We're several years, decades even away from that. But getting samples can really help us out with that. Um so we're gonna mostly stay on the moon this evening though, but I will be talking about a little bit about Mars later, a little bit of asteroids too. But essentially we're wanting to like put humans boots back on the moon. We're wanting to have a sustainable presence on the moon. And you might be looking at this image of the moon and you're like, why? It's just gray and more gray. Oh goody. But I will say though, the minerals at the moon, the geology of the moon is so fascinating, and there's still so much to learn about it. And quite a bit of lessons learned from the Apollo astronauts as well, as far as how to sample correctly. We've definitely had some whoopsies along the way. If anybody's interested about my favorite moon rock, feel free to ask that in the chat so that way I remember to talk about that later. But if we were to look at just the grand scale of just the Apollo missions, where did we go and collect? It's really not that much of the moon. Looking at this, if we were to stretch out the map of the moon here, I'm gonna change my laser pointer here. There we go. Um, Not exactly a huge swath of the moon. There's still so much of the moon to explore. Now, granted, where the Apollo astronauts landed were pretty safe space areas, though. These are very low-lying, very much crystallized lava plains on the moon, which is a whole nother fascinating topic. So by all means, there's so much cratered area that would not have been safe to land necessarily. But again, we're wanting to stay on the moon, we kind of need to understand the material properties of the rest of the moon. So it makes sense. And so even through planetary science, there's so many different kinds of missions. You got your flyby, where you have pretty much a fancy camera suite strapped to a rocket and then just keep going. You're zooming along, you're not stopping, you take as many pictures as you can, like a tourist at Disney, just keep going. And now you got an orbiter where you're staying, but you're pretty much above the surface. You have some sort of lander, which is okay, but you're pretty much, constrained to one spot. Crude is okay, but humans are complicated. So that kind of goes all into sampler type missions. Samplers require some sort of orbit. Samplers don't necessarily always have to be crewed. Most of the time they do, but sometimes, we're getting a little bit better about having purely robotic samplers. Some landers are also samplers as well, but we want to be able to return the samples back to us. I So again, just broad strokes here as far as like, well, okay, why do we even need samplers in the first place? We have all this data, right? We have flybys, we got the orbiter data. What more information could we possibly need? The problem is that missions need to advance at some point. They absolutely do need to advance about how to really better study the moon and Mars and even the moons out at Jupiter and Saturn and so forth. So for that to advance, we really need to advance our modeling. But even models can only take us so far. And so you have this kind of back and forth tandem, but again, it's not exactly the whole picture. You gotta need to do experiments, and this is where experimental research can really come into play with bringing samples back. How did we do? Did we maybe mess up? In which case, we need to improve that instrumentation. Maybe we need to improve our models to really hone in on, hey, you know what? We have this fancy rock from the moon brought by Apollo astronauts. We really don't have that many sample left. Did we do it right? Did we model this correctly? And so you have all of these talking to each other and advancing each other on. And so samples really help kind of advance every single trifecta part of this. So Armstrong, his birthday was actually just the other day, which was exciting. So happy birthday, Buzz. Or no, sorry, that was Buzz Aldrin, not Armstrong. Sorry. So I love this quote from Armstrong though. Geologists have a saying, "Rocks remember," and it's like that's so true for samples as we are taking samples back from asteroids and the moon, eventually Mars at some point. It can really tell us so much exciting stories about that particular planet. How did they form? Under what conditions did you find this particular rock? And so we're even using Earth as our own template, if you will. How did certain minerals form, and how do you find certain minerals? Any rock hounds in the audience here tonight? You need to understand your environment, right? You need to understand like, well, okay, where are you going to find the best quartz clusters and even diamonds. You go to Arkansas, right? You know not to go to Colorado. Colorado may have a whole different set of minerals. If you want to go for a certain kind of schist, maybe blue schist, you need to go to this particular part of the US and not over to this other part, So it's almost like you got to understand your environment to really hone in on, okay, I need to go find this mineral. I want to study about this mineral. Where is this mineral? How did it form? Is it under certain environmental conditions? Is it water-based mineral like opal? Is it, how did it crystallize? Do you have twinning? I'm throwing a lot of mineralogical terms out here, though, but it's also important for us too, as we're picking up these rocks and viewing it under a microscope. We're asking the same questions. How did this rock form? How did you little cute little rock, how did you get there? How did you form? And then what can you tell us about the bigger picture? So even just looking at some thin sections, this is just an example of a thin section from an Apollo sample under a microscope. It's beautiful, and I'll share with you the secret of how to find more images like this, because there's an online encyclopedia out there. But again, bigger picture, right? How does just something so small as minerals and how the growth patterns of some of these minerals of a single rock can tell us the bigger picture of what happened on the moon? So even just simple olivine minerals can tell us about the volcanics across the moon. Again, all of this is just crystallized lava. And so, how active the moon would have been volcanically in its heyday billions of years ago, how hot would the lava have been, how sticky and runny that lava would have been. There's some parts of lava on the moon that may have been foamy at some point, which is very weird. If you think of like the foam hand soap dispensers that sometimes restaurants or even if your own home may have that, think of that like foamy versus something that's a little bit more runny like Dawn soap, right? You can have completely different volcanism on the moon, and it's exciting. So real quick then with asteroids. Asteroids hold many different interesting mysteries through the solar system, if you will. So not only are the chemistries weird, but also their placement in the solar system can give us a clue. So really beautiful ones are Vesta and Ceres is technically a dwarf planet. But even just breaking this down, the different masses, different kinds of metals that we have here, um, every single bit of the asteroid belt, excuse me, between Mars and Jupiter have what we call a geochemical fingerprint. Basically, any rock in the solar system would have their own fingerprint, but asteroids in particular, each one have their own fingerprint. And we have almost like a fingerprint database, if you will, of these asteroids, and we're able to see what color they are and their mass, maybe the type of metal they are as well. Are they silicate rich? Are they heavier than that? And we get an idea as to like, oh, you know what? Maybe some of the more heavy metal ones, yeah, are in a particular part of the asteroid belt as opposed to maybe the lighter minerals, those that have like nickel, aluminum, and certainly lighter metals in that regard. So looking at all these fingerprints is really cool. Now, do we want to sample as many as we can? Absolutely. Anybody a Pokemon fan here? Gotta catch them all. But unfortunately, we don't have the means or the funding or the technology to do that. So now it kind of comes down to how do you pick and choose? How, where do you want to go, what you want to do? And then how can it get us to answering the questions about the solar system? So a big question we have too is like the undifferentiated versus differentiated here. So undifferentiated, you got more comet-like material. It's very salty and cold, ammonia. It is a very bizarre chemical. The same ammonia that you have in your cleaning products, by the way. Nothing, terribly complex about that as far as house cleaners go. But in the solar system, ammonia does some really weird stuff. So undifferentiated is essentially just think almost globular icy, slushy, snowball type. It doesn't really have a uniform shape in any way. Think of like a hailstone, if anything, versus differentiated. You got layers, you got different, maybe rock water interactions. Again, you got your ammonia. But it's still very cold, still salty in some way though, but a little bit warmer in the sense of being wet instead of frozen. Okay. And so looking at all these different kinds of asteroids like Bennu, we're still trying to figure out like, well, which one does Bennu really fit into? Ceres and Enceladus are more the differentiated. Certain comets are just kind of like, well, it could be kind of a little bit of both. Comet 67P here is certainly more of the icy bit, but are all comets really in the same category? We're still kind of trying to figure that out a little bit, which is exciting. So Bennu, thankfully, we do have some stuff left. Now, now the exciting part is like, how do we sample these? What do we do about it? And there's so many different weird types to do it. And so obviously well, I shouldn't say easy per se, because again, what I said was humans complicate things. Humans are also very expensive to send into space as well, because, health is important. How about that? So if anything, sending astronauts to the moon, picking up a rock and bringing it back is actually fairly simple in that terms. It's not cheap, but it's simple. You have astronauts go out, you pick up a rock, you bring it back. Okie dokie. Um, but you could also have the astronauts do core tubes as well. So this is some very exciting core tubes I'll get to in a moment. You can have, like I say, you can have landers where they'll have like a little itty bitty scoops, little itty bitty drills probably on the underside. They'll scoop it up and they'll do some analysis here and then rocket their way back to Earth. The Russians did that with Luna. Chinese are doing that with Chang'e. We're hoping to ride that bandwagon soon enough too. OSIRIS-REx I'll get to in a moment though, but OSIRIS-REx was really really fun. Can you imagine seeing something like this in the middle of a desert though? How spooky would that be? But essentially that's pretty much the sample canister and then padded like crazy inside of this capsule so that way it can land. You might be wondering that's a really weird shape and that's on purpose. And that's because part of this underbelly side was to help the heat shield. We need to have it kind of that concave shape happening here so that way we can disperse the heat coming off of it. This stuff is really fun to play with. This is called aerogel. Aerogel. Aerogel, what we like to call ghost jello. So aerogel is really light. It actually does feel like Jello. Never touch it with your fingers though, because the oils from your hand will actually disintegrate it. However, it's as strong, nearly as strong as carbon, and it is heat resistant. You can set it on fire and it won't melt. Um, so only your finger, oils are mainly the only thing that will disintegrate it. So aerogel is really fantastic for capturing the tiniest little particles that you pretty much just have these little discs of ghost jello aerogel on the outside of some sort of rocket or satellite, blast it off into space, take a few turns around the Earth, come back in, and you can get like solar particles and tiny little bits of asteroid dust stuck in this stuff. And that makes it really nice and easy. Like tiny CubeSats have done some wonderful stuff with aerogel. It's actually a pretty cheap option. Now back to these core tubes real quick. These are really quite exciting. The Hang on, that was the clock chiming there. So what's really exciting about these core tubes is that this was a program called ANXA. I'm not sure if I have a slide about ANXA or not. Whoop. Let's see, that might be. Nope, I don't. Okay, so ANXA is the Apollo Next Generation Sample Analysis. So what ANXA did was exciting. Back during Apollo, so we're saying early 70s here, we made a contract, if you will, that certain samples were not to be touched for 50 years. Um, this was a contract under NASA to have certain core tubes of material, uh, never to be opened. If anybody's done one of those like time capsules as a kid, you put some mementos in it, maybe a letter to yourself in the future, bury it in the backyard. It was kind of like that, where this letter is essentially like, thou shalt not touch these sample tubes for 50 years, because we knew at the time, we knew that our technology was going to advance enough to do something really cool with these core tubes. And they were right. So fast forward 50 years, we were able to open these up only like a year and a bit ago. And we used, before we even opened it, we put them in an X-ray CT scanner, because X-rays have gotten so powerful enough to scan through these metal tubes, and we were able to take X-rays of these core samples. How really cool is that? That was so amazing that we were able to do that. And we were able to see, like, okay, did our container system, how well did it hold up in those 50 years? We found out that we did have a little bit of leaks. How can we improve our container and like drill core systems in the future, especially for Artemis? How can we improve that kind of engineering and technology to make sure that we prevent any further leaks, or maybe we'll do another 50-year contract of like, don't open this cool tube up. Right now, I can show the really cool video here. So this is with OSIRIS-REx. Um, and boom. All right. Don't worry, I'll replay this video again. So on the left here is a computer rendering of what the OSIRIS-REx mission was supposed to do, which was essentially land pretty heavily with this arm here, and boop, it did a very hard boop, essentially. So what it did was, this container was open, and what it did was it smacked so hard. Let's see. Let me see if I can play it again. Because it's just, oh no. Ah, no. Hang on. Things are going horribly wrong here. Okay. Everything's fine. There we go. Okay. All right. So as this thing is opened up, we had a target in sight. It would grab as quick as possible. It bounced off the surface. And what was exciting is that this stuff is quite fluffy. You can see just how, boom, how fluffy all this material just kind of spattered around. And what was exciting is that we got so much material in that container that it was not able to close right away. It was a little bit of a panic, though, because it's not like it just stayed. As soon as it did a grab and go, another way to talk about it is called a touch and go scenario. So a touch and go. The touch and go was so fast and so rapid that it's not like we could just stay and made sure it shut. We had to like pretty much boop the asteroid so hard, collect as much, and then rapidly come back to Earth as fast as possible. Thankfully, we were able to close it. Now, opening it was a whole different issue, and that got really fun as well. But we were able to open it. This is essentially what the canister ended up looking like, was just all of this kind of powder, very large clusters of rocks here and there. We got so much. The minimum requirement to say it was successful was 60 grams of material. We got 121.6 grams. That is a huge success for us, that we had that kind of a touch and go pneumatic drill that we had for that. So exciting times for the OSIRIS-REx mission in that regard. Oh, hey, how about that? I do have a slide on ANXA. All right, well, all right, so that I'll just skip through that. So sample return missions. We've had quite a few, not just for the moon. Now we're wanting to do more with the moon, so that's still a very exciting part in that. But the thing is that we want to still learn about the other things, different kinds of asteroids, comet and solar wind, to learn more about what the heck is the sun sputtering out at us at a constant rate. Um, Yeah, I already said OSIRIS-REx. OSIRIS-REx is our latest US sample return mission. There's still plenty of international partners happening. Phobos with MMX, that's with the Japanese Space Agency. So there's still plenty to still have some fun with here. Mars sample return, I say in development, that's some hard air quotes on that one. Artemis, absolutely. We want to get back into having astronaut collection sampling techniques. OSIRIS-REx, like I said, was the pneumatic, so there's that kind of touch and go. But you can see all these different kinds. Here's your aerogel sampler there, drills and scoops and so on and so forth. Even the drills themselves have significantly advanced since um, the USSR Luna drills for sure. You might just be thinking like, well, a drill is a drill, is it a Black and Decker? Nothing like that. But just like the design and making sure it's efficient, making sure you're not going to damage the rock that you're wanting to bring back, that kind of sample, even just the purest sample design of a drill can take years to just advance and build and test and so on. So get back to our gorgeous moon. We're going to a part of the moon we've never been to before. It's going to be exciting times. It's a little scary too. We're going to the south pole of the moon. So this is the south pole of the moon. Again, the geology of this area is really quite fascinating though, but notice here is that there's still a lot of craters here, so even just finding a landing spot in this cratery pit of despair here is going to be a challenge all on its own. But notice though, it's quite dark, it's quite shadowy in some bits here. And so there's some craters here on the south pole of the moon that takes the phrase where the sun don't shine to a literal statement level there. So we call these permanently shadowed regions or PSRs. And the exciting part is that there's some really weird like mineralogy and chemistry happening in these shadowed areas. Now, the tricky part with these shadowed areas, these PSRs, they're extremely cold. So I typically work in Kelvin, but to put this into context here, we're talking negative 400 some Fahrenheit. We're talking as cold as Pluto in some of these PSRs. Very, very chilly, a bit nippy. So if we're wanting to send astronauts into these PSRs, we're going to end up doing this with robots first. We're going to do this with rovers first because trying to send a human into something that cold is going to take a lot of ingenuity. It's going to take a lot of interesting engineering, even just with the spacesuit themselves. So it's going to take a little while, but we do want to send rovers and sample return missions into these PSRs because if it's as cold as Pluto, we're not just talking about water ice here. Now, water ice is certainly going to be your main component though, but because there's still some weird temperature variability in some of these shadowed areas. Some places are shadowed only part of the time for the moon versus other times of the moon. The moon does go into like a summer winter cycle. Now, when I mean summer winter cycle in these shadowed areas, I mean colder versus colder, right? I mean, you're still very, very cold, but the chemistry involved with how cold it can be changes wildly with temperature. So water ice, like I said, is very much the strong component here, but not all of the water ice is pure. You might have a little bit of methane, you might have a little bit of carbon dioxide, you may have bits and pieces of all these different kinds of chemistries. And that really does bring out some really cool open questions that we still have as to uh, orbiters and models can only tell us so much. We need samples to really help us out here. So how are they formed? What type of volatiles, right? So what kind of ice are we dealing with? Different crystalline structures. We actually don't know the physical nature of this ice. They could be ice cubes for all we know. More likely not. But even so, if I were to say ice cubes, are you thinking like the bigger ice cubes that you may have in your home freezer out of an ice cube tray, or is it like the crushed ice that you might get from McDonald's, right? It's still ice cubes, but they're different sizes, there's different granularity. and so on. And so we're kind of asking the same questions here. What level of the ice is it in a physical form? How tiny is it, if anything? Are there differences in its freezing capabilities too? Can this be used as a resource? A really, really big question here is like, well, oh, hey, guess what? H2O, that's water. That's also, you break it apart, you got your hydrogen, you got your oxygen. Can that be useful as a fuel source? Can that be useful for long-term stay? So it all boils down to how in the world do you sample something as cold as Pluto after never having done it before? And so that's pretty much where we're at as far as like Artemis goes. You also have the CLIPS missions, which is the commercial landing payload services. So we're wanting to have more commercial partners team up with NASA to go to these areas. And so it's all about location, right? There's several spots all around the south pole of the moon, all these different orange outlined areas. All those have some level of water, but again, we don't know how much, we don't know how deep, we don't know how you know physical sample they are. I If we were to look at a temperature map of the moon, by all means, I wish the moon were this colorful instead of the 50 shades of gray that's on the moon. I wish it was this pretty. But no, so these are the temperature maps of the moon. And again, you have all these different kinds of ice that you could potentially have. Water being again that main component though, but all these different like purpley blue areas, the really, really cold stuff, you get some really, really weird stuff then. Yeah, here comes back our ammonia pal as well. Ammonia is everywhere, for sure. Now, with Artemis, we have narrowed it down to a few locations. With Artemis, it's still an ongoing process to really try to narrow down where do we want to go, what do we want to do when we get there, and so on. But absolutely, we are going to have samples to bring back because, hey, you know what? If we're going to send people there, you're sure to bring back rocks. They better bring back rocks. So there's an exciting group that's been around for several years now. It's called the Lunar Exploration Analysis Group, or LEAG. So we teamed up. I'm part of LEAG. We teamed up with the Extraterrestrial Materials Assessment Group, and we formed a sort of like white paper report. It's past review. It's about to be publicly available. So keep an eye out for that if you're more interested in like cold sample return. But essentially, this report kind of goes into like very open questions into the why and the how. So like what science might be lost because ice is so sensitive, it's gonna melt, it's gonna sublimate, it's gonna have damage to it. So how much is too much of a damage? A little bit of damage might be okay, but you're still gonna lose some level of science though. So how much is too much? I'm not gonna let you read this eyesore of a slide. So here's the overall general themes here is like what's with frost on the moon? How about the hydrogen? Can hydrogen be useful as a human resource in that regard? Is this hydrogen even usable in some way? Where did it come from? Where did this ice come from, and where does it go as well? Once it sublimates, does it kind of stay put and refreeze elsewhere? And so on. So learning about the chemistry, and then, yeah, how do you acquire samples? So we still have some of the capabilities from the Apollo um, sample core tubes and everything. The different sealants we've improved over the years. Vacuum containers. How do you pretty much you're sucking up the sample into these tubes and then airtight seals in that regard. Different kinds of drill geometry as well. We've improved through the Apollo sampling as well. The moon is really quite weird. The best analogy to describe um, the lunar surface is flour. So if you ever pick up a sack of flour, it's heavy, right? You ever try to almost like I never want you to say a pound flour, but it's hard, right? It could be a bit condensed if you try to just, smack your hand against a condensed bag of flour. However, you get a scoop of it to bake your cookies. It's quite light, it's fluffy, it gets everywhere. And so the lunar surface is very, very close to the analogy of flour, and that it's dense, it gets denser the deeper you go, but it's horribly light and fluffy. And so you make sure that you got enough sample to bring back and not just fluff off. So how does this work with like laboratory science, right? So sample science, we're bringing the rocks back. Now what? What can we do on the surface that we may not be able to do in a laboratory? And a big one is the solar interactions. This surface is constantly being radiated. It's sunburned, if you will, by radiation. And so, is there something with the sample that is tied in with radiation that may be lost by the time we bring it back? And so that kind of goes into a bit of contamination. So there's two major themes of contamination, natural versus induced. Natural, it's inevitable, natural hazards on the moon, kind of deal. So dust is a huge one, radiation is a big one, illumination and shadows is also a natural hazard, which affects your temperature. All of these essentially affect your temperature. So those are more or less inevitable hazards. So how do we make sure our sampling techniques can get around these problems, if you will, versus induced? It's so induced risks is something that we've accidentally brought upon ourselves. So how do we make sure we mitigate? We're very careful about it. Like leaks, right? You don't want your batteries to leak all over your sample, all over your landing site. You don't want your tools just left on the surface. That's considered contamination now. Even the astronaut suits. I don't mean just like walking around, astronauts are going to have to walk around, that's fine. But the suits themselves can also leak chemicals as well. So not great if that happens. So we make sure that we're aware of our environment, we're aware of how we sample these, and this applies to all activity. Okay, and when I mean all activity, I mean all activity needs to be in some form like assessed and evaluated and make sure we know what if we're doing. Because by all means we did it well with Apollo, but there was still quite a bit of mistakes with Apollo as well. And so we need policies, we need standards, we need rules, um kind of deal to bring stuff back. So as I keep saying, dust is awful. A good or rather a bad thing about some of these sealants is like dust can get into these cores, dust can get into those sealants and completely destroy those sealants and everything. I'm going to try to really rapidly wrap this up. But even though the dust may be awful as far as like astronauts and exploration goes, though there's still some really cool science to be had with dust. And so again, back to hazards though, like landing. There's a YouTube video that does this very well with the Apollo landing. At 130 feet, you get some beautiful craters as they're looking down. By 46 feet, you're already getting some really heavy dust plumes. By 18 feet above the very rocky, cratery surface, you cannot see anything. So you better hope that you're gonna land just fine. And from this landing, it's like, okay, I got some plume contamination happening. Okay, how bad can that be? Or remember how I was saying how fluffy some of this dust can be? 155 meters away, we had a surveyor camera already landed on the moon, minding its own business. This dust from Apollo 12, 155 meters away, completely covered this poor surveyor camera with dust that we had our astronauts walk over there and pretty much slide their finger across one of the camera lenses right here. That's their fingerprint streak. We completely covered this thing with dust. So is that really considered? What level of contamination is that really going to be? It's inevitable. It's a problem. So how do we make sure we mitigate it? And then that's all to say, are we really ready? Are we really ready to bring back volatile samples? The answer is no, we're not ready yet. We're working on it. So what does curation look like? How do you make sure that you're keeping something as cold as Pluto at a good temperature that you're not just gonna freeze, melt, freeze, melt, freeze, melt. You're losing sample in that regard. Sorry, I'm skipping some of these slides here though. But yeah, so contamination prevention is really good. But with that, with sample handling, you really got to define like how much rock are you able to bring back? What kind of equipment are you needing? Are we really ready with our technology? Again, we're not ready for cold samples just yet. And then we really need to make sure we've got our policies and protocols ready. What if something happens? Do we have emergency protocols ready? And then this kind of goes into what we call contamination knowledge, or the knowledge gaps, right? So we've done this before. We've done this with many samples before, Apollo samples, OSIRIS-REx. But all of these, again, are just kind of still advancing as we're still learning. And yeah, maybe the first few ice samples we bring back for the moon, we're probably going to make some interesting mistakes. And so I'll just wrap this up as to, like, why bring back samples? Again, what can this really tell us about the solar system? What can this tell us about our own technology advancements? What I don't have on here is what can this tell us about living on the moon and Mars as well? I will unfortunately skip through some of these. I do want to talk about Mars sample return real quick though. So this is still a huge question mark when it comes to current funding right now. Right now, Percy is doing great. It's still collecting samples. This part, this part, we're still unsure about because it's been collecting samples, it's been dropping samples like crazy. It's doing great. But to collect the samples and to then return them back to Earth, this is still a big question mark on this part. Otherwise, rover's gonna rover. But back to Star Wars real quick. This is actually what the sample tubes look like, and we love Star Wars. We're all nerds here, so we love saying that these are, oh my goodness, we're leaving lightsabers on Mars. In reality, this doesn't give you any sort of scale whatsoever. These things are centimeters, right? These things are tiny, tiny sample tubes. So not much of a hilt for a lightsaber in any regard, unless you want like a centimeter sized tiny creature lightsaber, then go for it. But these things are actually quite tiny. So like I said, I bet quite a few centimeter sized tubes to eventually get into a sample cache to bring back to Earth. So the technology is still advancing. We're still working on it. It's just how do we get there and how do we bring it back? It's still a big question mark right now. And then the next exciting thing we have coming up with Artemis is Artemis 2. Yay, we're launching in just like a few weeks, so we're very excited and very nervous for it. But Artemis 2 is not landing on the moon. I just want to make that clear. Artemis 2 is going to slingshot around the moon to get us ready to land back onto the moon. We haven't landed for over 50 years now. We kind of need to update our images, our mapping, our technology, and also make sure we really know where we want to go as well. So Artemis 2 is launching in just a few weeks' time. Exciting stuff happening there. And so if you want to see Apollo samples under a microscope and see all the really pretty rainbow pictures, or you want to print some out for your classroom or anything, feel free to look at this website here. It's all free. It's a beautiful gallery of different Apollo samples, thin sections, microscopes. It tells you more about like what mineral you're looking at, how big some of these samples are, and everything, different soils, different rock types, and so on. So highly encourage you for that. All right. So with that, happy to answer questions, but thank you all so much for sticking to the end with that. So I'm gonna stop sharing. Thank you.
Thank you very much, Caitlin. Do you actually have the 3 questions, the PDH questions to ask us?
Yes, or if not, I think Krista as well. But yes, let me pull it up, maybe. If
Well,
my
Caitlin is looking for that. If anybody does have some questions and they want to put them in the chat, go ahead and start doing that now. We'll hold off on people unmuting themselves to ask questions, just so we can make sure we get the three PDH questions in first. Or, Chris or Derek, if you guys can find them a little quicker.
Yep, I got the questions. Hooray. All right.
Go for it.
All right. Should I type them out or just say it?
Yep, just saying.
Cool. Okay. All right. So first question then. It can get really cold at the lunar poles in permanent shadow, as cold as blank. Excellent. Love to see it. Love to see it in the chat. All right, Regina, can you let me know when or Jennifer, if I'm able to go on to the next
Yeah,
question?
I think we've got enough responses if you want to give us the answer.
Yep, so it is Pluto. Woo! Good. I love talking about Pluto. And so I hope in some future time I could come back and chat with you guys about Pluto. That would be really cool. Similar temps here in Buffalo. It does feel like that. I know. Excellent. Okay. All right. Are we ready for second question?
Yes, we are.
Cool. Okay. Which is the latest US sample return mission? We landed in the desert with a capsule with no name. Oh, interesting. Ah.
By your response right now, I'm wondering if we all misheard this.
I'm wondering. I am wondering that. So latest sample return. We've actually had to bring back samples, physical samples, which we already have.
All right, I'll just give it a couple more seconds.
I mean, I saw one person got it right. So it's just like, oh dear. Okay, good. So now two people. Okay. Okay. Now people are starting to remember. There you
Now
go.
we're all going to start changing our answers. I'll throw that one in there too.
There you go.
Okay, I think you can give us the answer at this point.
Yep. Yep. Everyone's like, Osiris. Yes, it's Osiris Rex.
Okay, and your third question?
All right, third question. What I'm gonna slightly change my question on here. But what is the name of that ghost jello sampling technique that I had mentioned before? Yeah. Excellent. Hey, everybody knows how to spell it right too. Good. Good on you. A lot of engineering students don't remember how to spell it. It gets really entertaining. Yay. Okay. Yes. Yep. The answer is aerogel. Woo.
Excellent. Okay, people can continue to post their questions in the chat or get ready to unmute yourself. But the first question came in from Jean Florentino. When is the next landing on the moon being planned?
As my clock is chiming in the background. Right. So Artemis 3 is going to be our next like at least US sample return. So the Chinese have already done sample returns as of late. And Mark, I'll get to your question here in a moment about Chinese information here. But I as far as like bringing back samples from the moon, it'll be with Artemis 3. Give it another 2 years or so. There's still a lot to learn about this new orbit. Because we're going to the South Pole of the moon, the orbit and trajectory of how to get to the underbelly of the moon is really quite difficult. There's a lot of physics that even I don't know. So we want to make sure that our orbit is good and we're able to tackle that nicely. That's what Artemis 2 is going to do, is essentially dress rehearsal of that orbit with humans. So yes, we do have astronauts for Artemis 2. But Artemis 3, boots on the ground, we'll bring back moon rocks. Yay. But probably not ice, because we're not ready. We're not ready for that. But there was a fleeting question real quick about has there been any exchange of information / data with the Chinese with their recent samples? So yes and no. So if you are a university professor, if you are in a certain academic institution, you are allowed to write proposals to help with like data analysis, or you could be given like small samples kind of thing. Government agencies are not allowed. So even myself and under my particular contract, I am not allowed to have any like, nope, can't do anything with those samples, unfortunately. So I pretty much have to just kind of wait and wait and watch. A lot of us have to, unfortunately. That's just how politics are working right now. But the samples that they have retrieved, though, are really quite exciting, to be sure. So there should be some really cool updates probably in the next year or so. There's still quite a bit of analysis work to be done with that.
Okay, we had another question from Chris Wenzel. What about precautions for unknown biohazards being returned to Earth?
Yes. And I see Evan made a note here about the quarantining part. So thankfully we don't need to do the astronaut quarantine part anymore. We realized that was horribly overkill. But it was still funny nonetheless. Um, so as far as unknown biohazards, yeah, by all means, we do try to have as clean of instruments and sampling as we possibly can. We have gotten way better about the containment systems, bringing it back to Earth, and then rapidly trying to transport them into a laboratory where it's like clean rooms and the bunny suits and handling properly what kind of gases to have. So nitrogen is a really good gas to use when preserving a lot of these rocks as well. Now, granted, is that like 100% clean? Probably not. Are there still some unknowns for contamination? Yeah, probably, more likely. Especially for when we're getting into more long-term staying on the moon. Don't sneeze on the moon rock, right? I mean, so what's that going to look like going forward? When we're having to be living with these rocks for longer periods of time, kind of thing. So by all means, that's still an ongoing thing, but we've gotten better from the Apollo era.
Okay, our next question is from Michael Teeling. What phases of ice are you expecting to encounter at the moon's south pole?
Yes, I mean, we know it's going to be solid in some way. My guess is that it's going to be really itty bitty tiny little ice grains snuggled in to the lunar soil. Um, some of it might be a bit deep. I don't think we're talking too much of like stratigraphic layers. There might be some, like on the walls of some of these craters, there might be some layers. That would be really, really cool to see, like strat layers of rock and ice. But for sampling, just getting a scoop of this stuff, it's probably going to be really itty bitty. So phases, as far as like chemical phases go, yeah, I mean, water and carbon dioxide. I really hope for some of the weird stuff like hydrogen sulfide. The problem with hydrogen sulfide, it's a very finicky ice. It sublimates. Even if you just like look at it, it freaks out. So if it's there, great, but how to sample it and preserve it, that might take a that might take a little while.
Okay, next is Joe Gavin. One of the earlier slides showed previous moon landing and sampling locations. How much area did that cover in terms of acres or state size comparison?
Yeah, you know what? You'd be surprised just how small it really is. I think not just landing, but also like them just walking around. Um, we were afraid, you don't want to lose your astronaut, right? That would be really bad. So we didn't have them like really go too far out. Um, but as far as like walking around or even roving around, in a single area, only the size of a baseball field, really quite tiny. So you imagine, several of these baseball field sized areas on the moon. That's really quite tiny, right? So it was showing that kind of map, and it's like, look where we landed here, we landed here. Like those circles are big for a reason because it gives you a general context. But in reality, the area that we have explored is so, so tiny, just baseball field sized levels of tiny. So yeah, really not that much coverage though, but so many rocks that we brought back. It was still so cool.
All right, and sorry if I mispronounced this next name. Duane Cafferty, was the dusty camera cleaned?
Um, Clean-ish. We wanted to keep it dusty and brought it back. We only brought back one of the cameras. We didn't bring back all of them. But we wanted to see how bad that dust would have damaged because then we were able to use it as almost like a damage report. And learn more about the lunar dust in that case. So the glass was scratched, the dust got into crevices we didn't know were gonna get dusty. So that really helps us a lot to figure out like, ah, yeah, you know what? The moon is dusty. How about that? What do we do about that?
All right, the next question is from Michael McCann. Will other nations have sample gathering efforts in conjunction with NASA?
Yes, absolutely. So like I said, like the Chinese are already underway. The Japanese Space Agency wants to do a little bit more. The Canadian Space Agency, I think, is partnering with us for sample return. The Indian Space Agency is doing really well. I think they're wanting to do a sample return at some point, but I don't think they're ready just yet. So it is really quite exciting to see all these different countries come up with kind of their own designs, their own ideas as to like, well, we want to sample here, we want to sample here, and so on. So by all means, and like even just within the next decade, the moon is going to get really, really busy. So how do we make sure we're not going to step on each other's toes and that we work together kind of deal? That in itself is kind of an ongoing process. So stay tuned.
All right, we got some fun alien emojis from Olivia. Another question from Jean Florentino. Are there any new large craters uh, since that have formed since the Apollo missions?
So not necessarily large craters per se, but have we been able to detect new craters? Absolutely. So the Lunar Reconnaissance Orbiter has been keeping track. We have found not only natural craters, we've also helped find any accidental crashes as well. So which happens. If your orbit goes out of whack or some phase stage of your rocket goes wibbly woo, then yep, Lunar Reconnaissance Orbiter is going around and around and around with all these beautiful cameras that we're able to see not only fresh impact craters, which are really cool, but also human-made uh, rocket impacts as well. But I wouldn't necessarily call them large per se, but it is really quite fun to see natural craters versus rocket craters. Rocket craters tend to have more debris as far as like chunks of metal being scattered around. And so from like an impact point of view, that's actually really cool to see, but kind of sad a little bit too, because it's like, oh no, that's someone's rocket that someone built. Oh no.
All right, we've got one last comment in the chat from George. Thank you for your work. Enjoy your exploration and come back and tell us more about Pluto. And I think we will probably have that arranged at some point. I'm sure Chris will get in touch with you because I think we would love to hear about Pluto.
Yay! And Pluto's a planet, everybody. Hey.
Okay, we're gonna have a fight about that with Neil deGrasse Tyson.
Bring it.
Are there any other questions? Anybody want to unmute and ask anything?
Caitlin, I just want to say thank you so much. This was a really fun and well presented presentation. So we definitely appreciate you taking the time to share your work tonight with our association.
Oh, thank you so much for having me back. And also like, your future speaker about like the drilling sites and around the New York environment, like keep that in mind of like these are the technologies that we're wanting to do on the moon at some point in much larger scale. So like as your next speaker is talking about like drill exploration, it's like think about like, oh, that's cool. We could do that on the moon
Yeah,
at
we
some
could send
point.
the USGS up there.
Hey, you know what? We need more geologists for the moon. That's my honest opinion. We've only sent one. That's a fun fact. Of all the Apollo astronauts, we've only sent one geologist. That was Harrison Schmitt. That was Apollo 17. Yep. Yep, good old Harrison. Yeah, he's still kicking around. He still comes to like geology conferences and planetary conferences. He'll chat your ear off about volcanic minerals.
Maybe he can come give us a chat.
You know what? He's a chatty person, I'm sure.
Uh, well, thank you again, Caitlin. This was great. We really appreciate it.
Thank you so much for having me this evening.
And we'll see you for the Pluto discussion.
Sounds good. We'll make it happen.
All right.
Right. Thanks,
Thanks,
everyone.
everybody.